Welcome viewers to the fourth lecture for the online series of lectures for the course of Algebraic Topology 2. Towards the end of the previous lecture, we initiated the discussion on short exact sequence. We will begin this first segment of the fourth lecture with a theorem that gives the necessary and sufficient condition for a short exact sequence to split. Okay. So let me state the theorem first, then I'll prove it. Theorem 1. Let 0 to A1, A1 to A2, and then from A2 to A3, and then from A3 to the trivial group containing the zero element only. The map from A1 to A2 is denoted by phi, and the group homomorphism from A2 to A3 is denoted by psi. Okay, let this sequence be exact. The following statements are equivalent. 1. The sequence above splits. The second statement says that there is a map P from A2 to A1 in this direction such that the composition of P with phi is the identity map on A1. And the third statement tells us that there is a map J from A3 to A2. This is J, such that the composition of psi with J is the identity map on A3. Okay. All right. For the proof of this theorem, first we show that one implies 2 and 1 implies 3. Okay. So from the definition of the split exact sequence using external direct sum, it follows that it's sufficient to prove these two things for the following sequence: 0 to A1, A1 to A1 external direct sum A3, and then from this direct sum to A3, and from A3 to 0. Okay, this is the inclusion of A1 into A1 direct sum A3, and this is the canonical projection onto the second factor from A1 direct sum A3 to A3. Okay, all right. So now we are going to prove that this second statement is going to be true. To prove 2, so one takes P, right? This guy P from A1 direct sum A3 to A1 to be the projection onto the first factor, to be the projection onto the first factor. Okay, so in other words, if we choose an element from this direct sum, which looks like this, a1 comma a3. So under the action of p on this pair, we are supposed to get just a1. Okay, so that's p. And to prove 3, so one can check that this holds immediately. Okay, and to prove 3, one takes the map J to be the canonical inclusion, right? So J is supposed to be from A3 to A1, direct sum A3. One takes J from A3 to A1, direct sum A3 to be the standard inclusion map. Standard inclusion map. Okay. Okay. All right. And it's also straightforward that this holds under the definition of such a map J. Okay. All right. So we're done proving that 1 implies 2 and 1 implies 3. Now we'll prove that 2 implies 1. Okay. Let me erase this part of the proof. So I'm supposed to prove that 2 implies 1. Okay, so in other words, we have to prove that the sequence that we are studying is a split exact sequence. So for that, we are going to use the internal direct sum version of the definition of split exact sequence. So we'll just show that A2, this guy in the middle, this abelian group, is the direct sum of the image of A1 under phi and kernel of P. Okay, the kernel of this map P. Kernel of P. All right. And kernel of P is a subgroup of A2, and in the definition of split exact sequence, the subgroup B of A2 is just kernel of P. That's what we are going to prove, and that way we prove that the short exact sequence under study in question is a split exact sequence. Okay. Okay, let me write it. It will prove that zero to A1 to phi of A1 plus kernel of P, and from sorry, this is a direct sum, and from the direct sum of phi of A1 and kernel of P to A3, and from A3 to 0. Okay, the map from the direct sum of phi of A1 and kernel of P to A3 is psi, and from A1 to phi of A1, direct sum kernel of P is phi. Okay, and we are assuming that that 2 holds, and the map is in this direction, the map P. Okay, so first choose X, the element X in the group A2, and we write the element X in A2 as phi composed with P acting on X plus X minus phi composed with P acting on X. Okay. it is immediate that x is equal to whatever we have written on the right hand side, since p of x, okay, so it's given that P is a map from A2 to A1 such that P composed with phi is the identity map on A1. So given that map P, P of X is supposed to be in A1. P of X is in A1 and phi of P of X is in phi of A1, right? On the other hand, P of this piece, P acting on this piece gives us P of X minus phi composed with P acting on X is equal to, using the linearity of P, since P is a group homomorphism, P of X minus P composed with phi composed with P acting on X. Okay. And we know that P composed with phi is the identity map on A1, so this guy is the identity map, so that we are left with P of X minus P of X, which is just 0. Okay, which means that this part, this guy, this element is in phi composed with P acting on X is in kernel of kernel of P. Okay, good. So in this decomposition of X, we have seen that the second piece belongs to kernel of P. Okay, and all right, and we have seen that phi composed with P acting on X belongs to phi of A1. So the decomposition makes sense, okay, because the first piece belongs to phi of A1 and the second piece belongs to kernel of P. Now we are going to show that the intersection of these two pieces is just the zero element. Okay, so let me erase everything. I need room. Next, if X is in the overlap of these two pieces, phi of A1 intersected with kernel of P, then there exists an element Y in the group A1 such that phi of Y is equal to X, because X belongs to the overlap and hence X belongs to each of these pieces. So X belongs to phi of A1, and which implies that there exists an element Y in A1 such that phi of Y is equal to X, leading to the fact that P composed with phi acting on Y is P of X, which implies, since P composed with phi is the identity element, is the identity map on A1. Okay, and hence this is just Y. So we have Y is equal to P of X. Since X also belongs to kernel of P, one obtains P of X is equal to 0, which implies Y is equal to 0, right? Since Y is equal to P of X. Okay. And now, since phi is a monomorphism or an injective map, phi of 0 is always equal to 0. That is, Okay, so from here we get that phi of 0 is equal to x, and since we are supposed to have phi of 0 is equal to 0, we must have x to be equal to 0. One therefore finds the intersection of phi of a1 and kernel of P is just the zero element of the group. Hence, A2 can be decomposed as the internal direct sum of phi of A1 and kernel of P. Okay, good. Now, one needs to show that 3 implies 1. Let's get to the proof of 3 implying 1. So one is given this map J from A3 to A2 such that psi composed with J is the identity map on A3, and one needs to prove that the underlying exact sequence splits. Okay, and we do pretty much the same thing we did for the previous proof. We showed that A2 can be written down as kernel of psi internal direct sum J of A3. Okay, and since the sequence is exact, kernel of psi is image of phi, and that, so if we prove this thing, we'll end up proving that A2 is phi of A1 direct sum J of A3. That will prove that the underlying exact sequence splits. Okay, so let's get started with the generic element X in the group A2. We write X um, uh, as the sum of two pieces, X minus J composed with psi acting on X plus J composed with psi acting on X. Okay, this is straightforward. Now, since the action of psi on this piece gives us psi of X minus psi composed with J acting on psi of X, and psi composed with J is the identity map on A3, one must have psi, this thing to be equal to psi of X minus psi of X, which is 0. And that proves that this element X minus J composed with psi acting on X is in kernel of psi. Okay, so let me write down the sequence that we're studying. That helps. This is the sequence that we are studying. 0 to A1, A1 to A2, A2 to A3, and from A3 to A0. The homomorphism from A1 to A2 is phi, and the homomorphism from A2 to A3 is psi. And the map from A3 to A2, the given map, is denoted by J. All right, now for this element X in the group A2, look at here, look at this diagram, this short exact sequence. Since X is in A2, psi of X is supposed to be in our A3, the group A3. So that J composed with psi acting on X is supposed to be in J of A3. Okay, so which proves that this piece in the decomposition of X lies in J of A3. So let me write it. Therefore, in the decomposition of the generic element X in the group A2, X is equal to X minus J composed with psi acting on X plus J composed with psi acting on X. Okay, where this first piece X minus J composed with psi acting on X belongs to kernel of psi. We have shown it, and we have just shown that J composed with psi acting on X is in J of A3. Okay, now we are just left with proving that the intersection of these two pieces, kernel of psi and J of A3, is just the zero element of the group of A2. Okay, let me prove it. If X is an element here in kernel of psi intersected with J of A3, then since X is in J of A3, there exists an element, a group element in A3 such that J of Z is equal to X. We denote it by equation number 1, so that psi of X is, so we apply psi on both sides of equation number 1 to have psi of X is equal to psi composed with J acting on Z. And since psi composed with J is given to be the identity map on A3, it becomes just Z. All right. Now here X is in the intersection of these two pieces, so X is also in kernel of psi, and therefore one has psi of X is equal to 0. But we have proven earlier, a while ago, that psi of X is Z, therefore Z has to be 0. Okay. Now consider the map J, the given map. Consider J from A3 to A2. Right. Let J of X is equal to J of Y for X and Y in A3. Okay. So the images of X and Y under J are taken to be equal. Then we apply J on both sides of this equality, so that we have psi of J acting on X is equal to psi composed with J, psi composed with J acting on Y. And since psi composed with J is the identity map on A3, we must have X is equal to Y. This proves that J is a monomorphism or an injective map. Okay. Now from 1, this one, from 1, it follows that J of 0 is equal to X, and we have just proven that J is a monomorphism, and hence X has to be 0. Okay, so thus we prove that the element, a generic element of the intersection of kernel of psi and J of A3 has to be 0. There is no other non-trivial element in the group, in the intersection of these two pieces. Okay, so which proves that A2 is indeed the direct sum of kernel of psi and J of A3, QED. Okay, so we're done proving theorem of 1. Then there is a useful corollary to theorem 1. Let me state it and then I'll prove it. Corollary to theorem 1. Okay, let 0 to A1 and from A1 to A2, the group homomorphism from A1 to A2 is phi, and then from A2 to A3, where the group homomorphism from A2 to A3 is psi, and from A3 to 0. Okay, let this sequence be exact. If this piece, this group A3 is free abelian, then the sequence splits. Okay, so here goes the proof of this corollary. We choose a basis of this free abelian group A3 which we denote by this collection E alpha. So we are going to use theorem 1. All right. If we are done proving that the third part of the theorem 1 holds, that it will be done proving that this sequence splits using theorem 1. So we are just going to show that the third part of the theorem 1 holds true. Okay. So here is the sequence. Let me rewrite the sequence. Okay, and this is the given exact sequence, and we are going to add this map J to this sequence. All right, and we have to define this map J so that part 3 of theorem 1 holds. Okay, define the map J from A3 to A2 with the help of its action, of the action of this map, of its action on the basis element E alpha of the free abelian group A3. Okay, we let J of E alpha J of E alpha be any of the elements inverse image of E alpha under psi. Okay, all right, so here the basis elements are all here because A3 is free abelian. So we pick up a basis element E alpha, and J of E alpha is defined to be an element here, okay, which is the pre-image of E alpha under psi, the given map psi. Okay, this is how we define the map J by its action on the basis elements of the free abelian group A3. Okay. Now, given a generic element of the free abelian group A3 that we denote by the linear combination of these contributions n alpha e alpha. Okay, that is a generic element of the group A3, and J acting on such a generic element n alpha e alpha, sum of all the elements, sum of n alpha e alpha is equal to sum of n alpha. We are just pushing J inside, injecting J through the bracket, and then we have J times E alpha here. Okay, we stop here, and then let me raise this front matter. Then psi composed with J acting on this generic element of A3, sum of n alpha E alpha is equal to sum of n alpha, and then again we push psi composed with J inside. Okay, psi composed with J acting on E alpha, right? And J of E alpha is given as the inverse image of E alpha under psi, right? And we know that this guy does nothing on E alpha, right? According to the definition of inverse image n alpha E alpha. Okay, it proves that psi composed with J is the identity map on A3. Identity map on A3. So we are done proving that the third part of the first theorem holds true. And according to theorem 1, then the short exact sequence that we are studying must split. Okay. All right. So this is how we prove the corollary to the theorem 1. This is an important corollary. Now we will state a few facts which will be proven useful later without proving those facts. So let me write it. Certain facts without proofs. Without proofs. Okay. So let me state them without proving them. Recall that from, so I'm going to define a simplicial map first, recalling it from algebraic from the course of algebraic topology 1, from AT1, a simplicial map F from mod K to mod L, where mod K and mod L are underlying spaces, which are topological spaces corresponding to the complex K and complex L, respectively. Okay, so a simplicial map is a continuous map between the underlying spaces of the complexes under study. Okay, let me write it. Recall that a simplicial map is a continuous map between the underlying spaces of two simplicial complexes K and L, with G being a map between the vertex sets K of K superscript 0 to L superscript 0. This is the vertex set of the complex K, and this is the vertex set of the complex L. Okay, so this G being a map between the sets of vertices of the complexes, so that whenever V0 all the way up to Vn of the complex K span a simplex of K, the points f of V0, comma, all the way up to f of Vn these points will be vertices of a simplex L. Okay, which means that for a given point x in the underlying space of K, the continuous map f from mod K to mod L satisfies, so x is written as a linear combination of the vertices, right? Where Ti are the barycentric coordinates of the given point x. I runs from 0 to n, and this will imply that f of x, that will be a point in the complex L, and that should be written as a linear combination of the vertices G of Vi, which are vertices in L. Okay. Okay. Ti still remains the barycentric coordinates of the point f of x in the complex L. Okay. Okay, so we recall the definition of a simplicial map from the course of Algebraic Topology 1. Now, if we are given such a simplicial map, that map will induce a homomorphism at the level of the chain groups. Okay, let me give the definition of such an induced homomorphism. So here is another definition. Let f from mod K to mod L be a simplicial map if this guy V0 all the way up to Vp is an oriented p-simplex of K p-simplex of K, then the points FV0 all the way up to FVP span a simplex of L, according to the definition of a simplicial map, and we then define a homomorphism we then define a homomorphism f hash at P to be a map from Cp of K, the group of P chains on K, to Cp of L, the group of P chains on L, by defining it on elementary P chains. Elementary P chains corresponding to oriented P simplices of the complex K. F hash at P acting on the elementary P chain corresponding to the P simplex, oriented P simplex, this one, V0 all the way up to Vp. This is defined as f of V0, comma, all the way up to f of Vp if they are all distinct. If all of these points f of V0 all the way up to f of Vp are distinct, okay, and is equal to 0 otherwise. So if at least two of them are equal, we then have this map taking this elementary P chain to 0 here in Cp of L. Okay, we denote it by equation number 2. Now we have a very important lemma. We state it without any proof. Lemma 1. The first lemma of this lecture, stated without proof. So here we first write the chain complex Cp1 K and the boundary map del P plus 1 that takes Cp plus 1 of K to Cp of K, and then under the action of the boundary map del P, Cp of K goes to Cp minus 1 of K, and then acts del P minus 1 on Cp minus 1 of K, and goes on like that. This is the chain complex on K, on the simplicial complex K. Then we have another chain complex defined on the simplicial complex L, Cp plus 1 L, and then the boundary map del P1 takes it to C P of L, and the boundary map del P takes it to Cp minus 1 of L, and then goes on like that. Okay, so if you want to differentiate this boundary map, the first set of boundary maps from the second set of boundary maps, then you can put a subscript here, K, 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 and superscript, sorry. You can put the superscripts K for the boundary maps for in the first simplicial complex, and put the superscript L in the second set of boundary maps, L everywhere. Okay. All right, now the chain maps. The chain map is a family of group homomorphisms, right? We know that from the definition of chain map, and these are precisely f hash p minus 1, f hash p, f hash, sorry, this one is f hash p plus 1, this is f hash at p, and this is f hash at p minus 1. Okay, these maps, the elements of the family of group homomorphisms that constitute the chain map are all induced from the simplicial map F. Between the underlying spaces of the given two simplicial complexes K and L. All right. All right. So each of the squares here commute. The homomorphism f hash commutes with the boundary operator. So by that we mean that each of these squares commute, meaning that each of these squares is a commutative diagram. So let's just take this square, and we can write from the commutativity of this square, we write del P okay, so I'm taking right, I'm not taking this square, I'm taking this square instead. So we are writing del P superscript L, and then F hash at P acting on an element here, which is an elementary B chain. Let's write it here, V0 all the way up to Vp, and that is going to be equal to, using the commutativity of this square, we write it as F hash at P minus 1 of del P K V0 all the way up to Vp. Okay, good. Therefore, F hash induces a homomorphism. We have seen in the previous lecture that whenever such diagrams all commute for two chain complexes talking to each other by a chain map, we have the boundaries taken to boundaries and cycles taken to cycles under under the induced homomorphism, meaning that this induced homomorphism is a homomorphism at the level of the homology groups. Okay, f hash at P is a map from HP of K to HP of L. Okay, so we see that we have an induced homomorphism at the level of the homology groups when F is a simplicial map between the underlying spaces of two simplicial complexes. We can have this induced homomorphism at the level of the homology groups. Okay. So this is the statement of lemma 1. I'm not going to prove it. For proof of this lemma, lemma 1, refer to section 12 of the textbook by Moncrief that we are following for this course. Okay, all right. Now, this was lemma 1. I'm not going to state lemma 2 here. Let me take a break at this point. I'll be back with more results on this stuffs. Okay, thank you very much for attending the first segment of the fourth lecture.